before digging into the logs, let's deal with this little topic that is complex roots. Okay, so we have complex roots. Now, what actually does it mean when we talk about the complex roots? Okay, let me tell you. We have a function f of x equals to x squared plus 1. Now, this is a really decent looking function. If I'll try to sketch the graph of this, it will look like this. We already talked about that in the first video. It has to look like this. Okay, this is x squared plus 1. But one important thing about this parabola is that it never cuts the x-axis. That simply means there won't be any real values or there won't be any real roots. Okay, so that means there should be another root that's called the complex root. Okay, how to find it? Simply, we are going to use the quadratic formula. If we're going to use the quadratic formula, it's minus b plus minus discriminant upon 2a. Now, here, I know that minus b term isn't there, x term isn't there, so that means b, the coefficient of x is 0, so that's 0 plus minus 4ac, 4 into a is 1 and c is 1, so that means it's minus 4, because it's minus 4ac upon 2. Now, I don't need to write 0 there, it means 0 plus minus root 4 into minus root 1. This minus root 4 can be written as root 4 into minus root 1, okay, upon 2. Okay, again, this root 4 is 2 and 2 cancels out. I'll be left with minus root 1 and along with the plus minus. So this will be plus minus root 1. And minus root 1 is called by some other name. It's called iota. So plus minus iota. Instead of minus root 1, I'm writing iota. So simply minus root 1 is called iota. I is denoted by I. Okay, so I replaced it with that thing. Now this plus minus, actually we have two roots again here, but these two roots are complex roots. Okay, later on we'll discuss about that, what actually are complex roots. This is a basic introduction here when we'll talk about the complex numbers itself. Okay, let's keep moving. Now let's dig into the logs. Okay, the first thing that we're going to deal here, talk about here is going to be about the exponential function. It's going to be exponents. Now, exponential function. You already might be knowing what an exponential function is. An exponential function is a function that's raised to a power. For example, a to the power of x equals to n. Okay. Now, that simply means we are raising a to the power of something. We're getting a number n here. Now, the most important thing here to realize is this, that a here, normally a, has to be taken as positive. The base here has to be taken as greater than 0. And not only that, I can't take a base to be 1. A here, the base here, cannot be equal to mathematically 1. Now you might be wondering, wait a minute, if you're clever enough, you might say, wait a minute, why can't I take base 1? Because if I will take base as 1, think about it, okay, I'm taking a as 1, instead of a I'm taking 1, because the base I'm plugging here is 1. Now, you have x here, so let's suppose we have x. Now think about it, if I raise 1 to power of anything, it's always going to give me 1. So no matter what I raise 1 here to, because this x can change, but if I change x, if I, for example, I raise 1 to the power of 2, 1 to the power of 10, 1 to the power of minus 1, the value that will come out to be here will always be 1. So that's why we don't take 1 as a base, because the value that will always come out to be here is 1. So it will be too much boring because we only will get one value. So that's why in exponential functions normally we don't take 1 as a base. Okay. Now that was the second important thing. Okay. Okay, this power can be anything. This can be negative, positive, depending upon what values we have to get out of it. Okay. Now, we can write it in the form of log. But one more important thing here that I should let you know about is that if we have an exponential function a to the power of x, now we take normally base as positive, so this is 2, I suppose 2 here, and we take it to the power of 2. Now it comes out to be 4. Now think about it, that we have a base here. The base is a positive number, the power is a positive number, and we got a positive number here. So that means if we have a positive number in the base, we have a positive number in the power, we're always going to get a positive number. That's pretty important. Not only that, think about it. Again, if we have a positive number in base and negative number in power. Now 2 to the minus 2. Now this 2 to the minus 2 can mathematically be written as 1 upon 2 to the power of 2. If I take the reciprocal, it looks like this. 1 upon 2 to the power of 2. Now 1 upon 2 to the power of 2 is 1 by 4. So I can write it as 1 by 4. Now think about it. 1 by 4 is a positive number. Now this 2 to the minus 2 here can be written as 1 by 4, which actually is a positive number. So that simply means if base here is positive, the power is negative, we're simply going to get 1 by 4. Okay, we're simply going to get positive. That means second conclusion comes out to be here that if the base is positive and the power is negative, we'll still get a positive number. So that is pretty important thing, pretty important conclusion. No matter what the power of the function will be, okay, if the base is positive, assuming that base is positive in both cases, bases are positive, you can think 2, yeah, 2. So we have positive bases. No matter what the bases, if the bases are positive, no matter what the powers will be, positive or negative, it will always give me a positive number. So this is an important conclusion, okay? That simply means the number n that pops out here will always be a positive number. Think about it. This is a, this is doing the work of x here, and the work of n is doing this 4 number. And in this case, when I took the power to be negative, this is doing the work of x, this is doing the work of a, and this one before is doing the work of n. That means here again, n came out to be positive. This is n here, and this is n here. In both cases, n came out to be positive. That means n has to be always positive if the base is a positive number. Okay? So let's see what actually the log means now. So what will be a better definition? For me, this definition has worked for a long time in my opinion. Well, I remember it this way. Log is an exponent. Now what does it mean? It means, for example, we have log base 2 4 equals to question mark. Now it simply means what should I raise 2 to? Here is the power. The answer of the log is actually the power, is a power. What should I raise 2 to? What should I raise 2 to? Here the answer is actually the power. I need to find out the power of this thing. I need to find out the power of the base of the log. So what should I raise 2 to in order to get 4? So that means I need to raise 2 to the power of 2. So that means the answer here will be 2. It's pretty simple. Now I can write it in the exponential form as this. If we have like this, if we have a function log a, okay, we have log a, x equals to n, I can write it as a should be raised to the power of n, and I will get x. So it can be mathematically written in the exponential form as a should be raised to the power of n, it will give me x. Simple as that. So whatever the base is, raised to the power of this number, whatever is on the other side of log, and I'm gonna get this answer back. Simple. So for example, we have log, again 3, for example 9 is equal to question mark, suppose 2. So that means 3 has been raised to the power of 2 and I got 9. So it can be written like this. 3 has been raised to the power of 2 and I got the answer 9. And that's mathematically correct. That's what actually the log gives.